Hello, today we're going to talk about structure 2.3.3. This is a higher level only topic. It's all about transition elements. So let's quick review the metallic model where you're going to have positive metal ions where the valence electrons of those metals are free to move around. And so they're not stuck with one particular nucleus effectively. They're delocalized. Ooh, I can spell. Delocalized. Okay, so the electrons are free to move about, which gives it some really unique properties, and the same is true for all kinds of metals, not just transition metals. What's a little bit unique about transition metals, and we're going to focus on the first row of the transition metal section. So we're looking right in here and specifically in this range. This is the 3D sublevel, which is right next to the 4s sublevel. And so with that 3D sublevel, it is very, very close in energy to that 4s sublevel. And that gives rise to some really interesting properties for transition metals. So they're really, really close in energy. That means they can move, the electrons can move between the 4s and 3D, depending on what's going on. So yes, the metallic model is still important for transition metals. But what makes it more interesting and unique is that the electrons are very close in energy between that 4s and 3D. One of the ways that the transition metals are unique is that they can have variable oxidation states. And now what that means is that you can have your electrons in your 4s and your 3D. Let's draw like this. Those are your 5 3D orbitals. If I have something like zinc, for example, zinc has a completely full 4s and a completely full 3D. So zinc is not considered a transition metal because when it forms an ion, it's going to lose the 2 electrons that are in the 4s, and it will be a +2 charge. However, when you have something else like, let's say, copper. Actually, let's do nickel because that's my name. So nickel has 4s and 3D as well. And there's your 3D. So if I were to fill this normally for nickel, and we're just looking at the valence electrons, it would fill like this, and that would be it. Because it's a transition metal and 4s is very close in energy to 3D, what really happens is that those electrons are instead filling up the 3D sublevel and leaving the 4s. However, when it forms an ion, it can form a number of different ions. Nickel can actually form a 2+ ion, it can form a 3+ ion, it can form a 4+ ion. Now some of these are more common than others, but that's because if it's losing 2 electrons, it can lose the 2 electrons there. And the electrons that are remaining when it's a 2+ ion can move around. So you might see some of the electrons maybe half filling your 4s orbital. Or you might see an electron filling like this. And then it could switch back, which is unique. So basically, the transition metals have different options for how they're filling those 2 or sublevels. And that's going to give rise to a variation in oxidation states. So it's kind of cool. I wouldn't go and memorize a whole bunch of different oxidation states for these transition metals. Understand that zinc is not because it's completely full. But all the other ones can form at least 2 different oxidation states. Like scandium can form a +2 and a +3 oxidation state. Copper can have a +1, +2, and +3 oxidation state. So there's a lot of different options for the different transition metals. Okay, so let's talk about some of the properties of transition metals. You're going to have some of the same properties as you will with any metal. Like the electrons are free to move, so they're going to conduct electricity. They're going to be good conductors of heat. They're going to be fairly malleable and ductile. But one thing that is a little more interesting is with melting point. So typically when we're talking about melting point with metals, like if I wanted to compare solid sodium with solid magnesium, the magnesium ions have a +2 charge versus the sodium ions have a +1 charge. The magnesium metal is going to have a stronger force of attraction because of that increased charge. So you'll see a very significant difference between the sodium and magnesium. When you go to look at your transition metals, let's compare like scandium with titanium. They are right next to each other on the periodic table. You're not going to always see scandium having the same exact oxidation state at all times. Scandium can form a +2 oxidation state and a +3 oxidation state sometimes. Titanium can also form a +2 and a +3. It can also form a +4. So depending on the oxidation state of the cations in your metal, you're going to see a variation in melting point. So effectively what I'm getting at is as you go across the periodic table from left to right, you're going to see a change in melting point for the representative elements. So groups 1, 2, 13, 14, 15. But if you go through the transition metals as you go across, you won't see as big of a difference in melting point. It actually forms kind of a weird pattern if you look at it, but I wouldn't necessarily go in and memorize it, but just have this idea that because there's different oxidation states, it's not going to follow the same trend. So why then do transition metals tend to have really high melting points compared with the S&P block metals? Well, there's a really large number of delocalized electrons because it includes the 4s and 3d electrons. So that leaves the positive ions, the cations, tend to have a larger positive charge as an overall rule. So even more so than our assigned oxidation state, because there's so many electrons that are free to move. Alrighty. And so the increased positive charge for the cations means that there's going to be a stronger coulombic attraction between that positive cation and the delocalized electron. And stronger coulombic attractions means it's going to take more energy to break them apart. And that leads to why transition metals have a really high electrical conductivity. Same reason. You have a really high number of electrons that are in the 4s or 3d sublevels. And because there's just more electrons that are free to move around, it allows it to conduct electricity very well and very easily. And so that's why you'll see things like copper used as wires in electrical components because it can conduct electricity super effectively. And so we talked about this a good bit before, but this links to, I believe, structure 3.1. But why is the trend in melting points of metals across a period less evident for the D block? And that's because those transition metals can form those variable oxidation states. And so it's kind of a less obvious difference between the transition metals as you go from one element to the next, because the electrons aren't necessarily like being lost at the same pace, if that makes sense. There's not always a 1 electron difference each time you move down. Whereas when you're going across the representative elements, there's definitely 1 electron difference as you go across.